Welcome back, casual gardeners. Today I'd like to talk to you about soil pH as part of my gardening science series, but it's a little chilly out here. Let's go in the greenhouse where it's warmer. Have you ever wondered why some plants seem to prefer acidic soil and others prefer basic soil? What makes soil acidic or basic in the first place? Why did we do 7 on the pH scale for neutral? I mean, it's 7. Does it make any logical sense? Not if you don't know chemistry. And what can you do if your soil is so alkaline that there's not enough acid at Home Depot to change your pH? Are you doomed to never grow the plants you want to grow? So my goal today is to answer all of those questions and more. Let's get started. So what is pH? Before we start talking about it, we should probably all agree just what it is. Outside of a chemistry lab, pH is basically the concentration of hydrogen ions in a solution. Soil is not a solution. It's chunky. But when water passes through soil and dissolves chemicals from the soil, it becomes a solution and can have a pH. 7 is a neutral pH, below 7 is an acidic pH, and above 7 is alkaline or basic. Those are synonyms. pH is a logarithmic scale, and that means that on the pH scale, each whole number increment is 10 times higher or lower than the one that comes before or after it. So a good example would be my soil pH. My soil pH is about 8, and it's that way through most of Utah because most of the state has a very similar geological history. What that means is that the pH here is 10 times higher than the optimal pH for garden soil. So I've had a little practice dealing with a high pH. There are some plants that are adapted for higher pHs or will at least tolerate them. But what does that really mean in terms of concentration, and why? Why is 7 neutral? Let's answer that question with another question. Did you know that pure water is simultaneously an acid and a base? Water does a weird little trick that involves randomly splitting a tiny fraction of its molecules. The H2O becomes a positively charged hydrogen ion and a negatively charged hydroxide ion. These ions also randomly recombine back into water molecules. Chemists call this balance between water molecules, hydrogen ions, and hydroxide ions the autodissociation constant. At standard temperature and pressure, the autodissociation constant is 1 times 10 to the negative 14th. Standard temperature is 25 degrees Celsius, which is about room temperature, and standard pressure is 1 atmosphere of pressure, or the pressure at sea level. Okay, don't freak out. I'm going to show you some chemistry math. You don't need to understand it. Just let it wash over you if you want to. When chemists are getting mathy, they use square brackets to mean concentration. The autodissociation constant of water at standard temperature and pressure is expressed like this. The concentration of hydrogen ions times the concentration of hydroxide ions equals 1 times 10 to the negative 14 moles per liter. A mole is not an animal in this case, it's a chemistry counting number. Because there tend to be a lot of molecules involved in a chemical reaction, it's a very big number. Approximately 6.023 times 10 to the 23rd. 18 milliliters of water contains 1 mole of water molecules, about 600 billion trillion molecules. A mole of bowling balls, which is a thing you could do, would be approximately 50 times more massive than our moon. A mole is a very, very big number. So in pure water, there is a concentration of 1 times 10 to the negative 7 moles per liter of hydrogen ions that just randomly split off the water. pH just means take the negative log base 10 of the concentration of hydrogen ions. We can plug that into a calculator and we find that the negative log base 10 of 1 times 10 to the negative 7 is 7. So even though 7 is a stupid number to represent the middle of a scale, it's based on real values from nature. So chemists are stubborn and won't change it, and we're all forced to go along with their tyranny. I promise that is the scariest part of this video. So the worst of it is over. I apologize if I triggered any former chemistry students with PTSD. Thank you for following along. It is kind of cool to know that 7 isn't just an arbitrary stupid number. It's a stupid number based on how stupid reality is. So why is soil pH so important to plants? Big picture, most nutrients are going to be available at lower pHs. Some nutrients are more available at higher pHs. But overall, lower pH, you get more nutrients. Higher pH, you start to have to do without because they're not dissolving into solution as readily. A good example of pH affecting how well things dissolve from current events would be the water in Flint, Michigan. So in Flint, Michigan, they changed water sources to a water source with a lower pH. And at that lower pH, the lead in their pipes dissolved more readily into solution, and they started having issues with lead poisoning. And this is the reason why, even in municipalities with newer pipes, there are still usually regulations that say you got to keep the water alkaline. So when somebody tries to sell you bottled alkaline water, you really don't need to buy that because you're getting that straight out of your tap. Plants mostly access minerals that are dissolved in water, and minerals dissolve most readily in water that is slightly acidic. If the water gets too acidic, it may leach those minerals down past the root zones of the plants and they will be unable to access them. Now, sufficiently acidic water will also make phosphorus and molybdenum unavailable to plants, even if they're right there where the plants can reach them. Some minerals like aluminum and manganese will become toxic to plants if the pH is low enough, because they dissolve so readily at lower pHs. Now, if the pH gets too high, most minerals will simply fail to dissolve and won't be available to the plants at all. And that is, in a nutshell, why soil pH is important to plants. Even at a perfect pH, plants will still need to do a little bit of work to access the nutrients required for growth. Some plants do almost all the work themselves. A lot of plants will make trade deals with their soil allies, and some plants will actually steal the nutrients they need from others. In most cases, plants will improve their nutrient access by sending out deeper and broader root networks. They'll also give off chemicals called root exudates. Some of those exudates are signaling compounds that will tell their soil allies to grow towards them so that they can make those trade networks. Some plants go dark, and their signaling root exudates are a lie. They will use them to con soil allies into forming networks with them, and then they will simply steal the nutrients they need. A lot of terrestrial orchids will actually do this root piracy thing. Some root exudates are chelating agents. A chelating agent wraps around a nutrient and keeps it available in a broader range of pHs than it would normally be available in. Iron and zinc are both really good examples of nutrients that need that chelating agent to lock them up and keep them available, because they're going to fall out of solution outside of a pretty narrow pH range. Some root exudates directly or indirectly change the soil structure around the roots. They're going to do this either by attracting and nourishing soil microbes and fungi, or they may improve the water retention of the soil, or they may even improve the drainage of the soil, depending on the needs of the plant. Generally speaking, plants that grow in acidic environments and only in acidic environments will have simpler root systems and will produce fewer root exudates, while plants that can adapt to a range of pHs or even prefer a more alkaline soil will grow a more extensive root system and will produce more types of root exudates and will produce a greater volume of root exudates. Now that we've gone way TMI about what soil pH is and how plants adapt to it, let's talk about what we can do about our soil pH in our gardens. If your soil pH is acidic, that's actually pretty easy to deal with. You can add crushed or powdered limestone to your soil. It's composed of calcium or magnesium carbonate, and in your soil it's going to act a little bit like baking soda by reacting with those acids and neutralizing them and bringing your soil pH up closer to neutral. But you want to be careful when you're adding limestone to your soil, because if you overshoot and your pH goes too high, it's a lot harder to bring that pH back down than it was to bring it up. If your soil is alkaline, I actually recommend not trying to change its pH. Alkaline soil is often the result of hundreds of thousands, if not millions of years of environmental processes that are contributing literal tons of carbonate salts to the soil. So a good example would be my home soil here in Utah. Utah soils can be as much as 15% to 40% carbonate by weight, which is a lot. It would take literal gallons of strong acids just to neutralize all of that buffering capacity in the soil and begin to bring the pH down. Meanwhile, all of that acid is killing all the life in my soil. Even after spending all of that time and money neutralizing my alkaline soil, it would still be interacting with my alkaline hard water, and it would still be interacting with my alkaline soil outside my garden beds. And over time, it will become alkaline again. Meanwhile, all of that fiddling that I'm doing with the pH is causing pH spikes and pH drops over and over again, and forcing my plants in my garden to adapt to constantly changing pH, which means that even the adaptable plants are going to have to be spending energy that they could be spending on growing, adapting to my help instead. Instead of directly trying to change pH in alkaline soil, I believe it's better to change your soil structure. And mostly I do this by adding a lot of organic matter and gardening in a way that encourages soil structure to naturally form and nourishes a lot of that soil life and a lot of the soil allies that will help our plants in our gardens have the energy and assistance that they need to deal with the alkaline pH. Now, I directly add organic matter to my soil by mulching with compost. I'll do a 2 or 3 inch layer of compost just as a mulch on top of my soil once or twice a year. I also try to indirectly improve the organic matter in my soil by doing a thing called the chop and drop method when the useful life of a plant is done. So what that entails is I will cut off the plant at soil level. If the plant tissue is healthy on top, I may leave it lying on top of the soil, and I will definitely leave the roots under the soil. Those roots decomposing in place are going to be leaving those root exudates where they were exuded, and also as it breaks down, it's going to be releasing a lot of the nutrients that were concentrated in the roots back into the soil to help the other plants that I plant next. Now, if you're growing in a place that has a lot of slugs or snails, your pest control methods may involve keeping your beds tidy, and the chop and drop method isn't tidy. So you're not going to want to leave those plant tops on your soil, and that's okay. You can take the tops and throw them in your compost pile and leave the roots in place. And just leaving those roots in place will give you some of the benefits of chop and drop without providing habitat for slugs and snails. Watering less frequently and deeply with drip irrigation is also going to do a lot to improve your soil structure. If you top your garden beds with a mulch of some kind to help lock that moisture in, that rich soil life is going to be contributing to your organic matter content all the way up to the surface. I admire Charles Dowding's no-dig method of gardening. It's not 100% effective in all soils. If you have heavy clay soil like mine, you will at least need to disturb it initially to break things up enough for those roots to get down in there and start building good soil structure. But a lot of the no-till methods are good for our garden. And trying to minimize our disturbance of the soil gives the soil microbes and the root networks and the mycorrhizal fungi a chance to really get established, and all of those are allies for the plants that we are growing to eat. Sometimes the best way to help our plants deal with suboptimal soil is to let them deal with it. That's about what I wanted to share with you today. Let me know in the comments if that was helpful. Make sure you're subscribed to my channel. Click that little bell so you get notifications when I post a new video. Thank you so much for joining me in my garden today, and I hope you have a wonderful time in your own.